Okay, in this video, we are going to demonstrate how these different functions transform in the D3 character table with the symmetries that they do. So when we derived this character table in a previous video, we actually didn't end up using any of these functions. So I thought it'd be useful to show why these functions have the symmetries that they do. So let's draw out a axis system, x, y, z. And we know that our principal rotation axis, the C3, always has to be defined as on the z-axis. So if I think about the z function first, that's going to be represented by a z vector. And so, of course, if we do identity operation on the z vector, that's going to get us z going to z. And then we take the trace of the 1 by 1 matrix that explains this transformation from z to z. That's just 1. We take the sum across the diagonal, the trace or the character of it, and so we get a value of 1. If we go to the next class, which is the C3, that's a C3 operation or a C3-2. It doesn't matter which one you choose. That is doing a rotation across the z. If we rotate a z vector, we're just taking a piece of string, you can imagine, and we're just rotating it across the axis that it's in. So that's not going to change the direction of the z vector. So z again is going to go to z. And so again, we get this 1 by 1 matrix that explains that. And the character, or chi, is what we write for the C3 operation, is equal to 1, which is why we have a 1 up here. Could write up here chi of the identity equals 1, which gives rise to that one. Chi just is a Greek letter we like to use for character. Okay, and our last one is the C2. And the C2, we have 3 perpendicular C2s. And we can, they're perpendicular, so they're in this XY plane. And we can define them sort of however we want, where the X, Y is. We know that they're going to be offset from one another, but let's just define one of those as being on the x-axis. So that's going to be rotating along the x-axis. So it's going to be a C2x, basically, we could write. And so the C2 then is going to take that, and we're spinning it now along the x. So that's going to take that z vector and flip it down, right? Because we're spinning across this x-axis. So that's going to take z to negative z. And so our 1 by 1 matrix is going to be a -1. And so our character across that is going to be -1. And so that's why we have z transforming as A2. Let's do the same thing for RZ. Sometimes I don't go over the rotation vectors, but I think it's good to show you an example of how the rotation vector symmetry works. And so what the rotation vector is, RZ, is actually the act of rotating. It's in a vector along whatever axis it is. So this is on the z. So that is the definition of RZ. Now, we do identity on that, we always get back the same thing. So RZ is going to go to RZ in a very analogous way. We're going to get chi equals 1. If we do a C3 on it, RZ also goes to RZ. Let's think about what that means. That means we have this vector right here, and we just did a 120-degree rotation on it. So the head, we're along the z, right, along in this direction. So the head and tail shifted positions a bit. So maybe it looks like, that's not the best drawing. Maybe it now looks like that, 120 degrees. But fundamentally, the vector is still denoting the same thing, which is the direction of the vector has not changed. And so RZ went to RZ. And so we still have a character of 1. Lastly, a more interesting case is when we do this C2. And remember, we said it was a C2x, so it's flipping it this way. Now, if you imagine you have this vector and you just flipped it that way, and And so what that's going to do is we started off with a vector like this, but we are flipping it kind of across here. We're doing a rotation there. And so what that ends up doing is it exchanges the positions of the head and the tail. And so where you had the rotation vector going in one direction this way, now you have the rotation direction actually changing. And so that means that RZ went into negative RZ, and that's why we have a -1 here, and the chi being -1. And so RZ also transforms like Z in A2 symmetry. Okay, let's do now XY. You can see that X and Y transform together here. I'm going to redraw out our axes here, just so we have that ready in case we need to visualize anything. But they transform together, and so that's not immediately obvious when you do an identity. X is going to go into X. You're looking fine, but then when you start to do a C3, right, you're doing that 120-degree rotation. It's like, oh, I have an X vector here, and I'm going to do a 120-degree rotation. That's going to get me a vector that looks something like this, 30 degrees off from the Y. I have to describe this vector in terms of X and Y. So X and Y are going to be together linked. And so because of that, then when I describe the identity, I really need a 2x2 matrix, X and Y being linked together. And we use the identity matrix with ones across the diagonal. We take the trace or the character across that main diagonal, and we get chi of identity is going to be equal to 1 + 1 = 2, and that's why I have a 2 here. But let's now do this for C3 to try to get this -1 value. For that, we're going to have to use the rotation matrix. So there's some trigonometry here. In the rotation matrix, we can use this in radians or degrees. I'm going to do radians. So 2 pi is 360 degrees divided by 3, so that's a C3. It's cosine 2 pi over 3 minus sine 2 pi over 3 and sine 2 pi over 3 and cosine 2 pi over 3. This equals -1/2 and -√3/2 and √3/2, just our trigonometry here, and -1/2. And so our character here of this matrix is -1/2 plus -1/2. So our chi of C3 equals -1/2 plus -1/2, which equals -1, which is what we got there. So that's matching, and we're on our way to proving that X and Y transform together as the vector E. Let's do now one of the perpendicular C2s. We liked doing this perpendicular C2 defined along the x-axis. So what's that going to do? Let's think about this. Well, X and Y have to transform together here. We know we're going to have a 2x2 matrix. And what is X going to do? Well, if we have an X vector and we're doing a rotation along the X, X is not going to change. X is going to stay the same. Just like when we're doing a C2Z along the Z vector with the Z vector, it didn't change the same. We're doing a rotation of that vector along the Z vector. So, this isn't going to change at all. However, the Y vector, which I will denote in a different color here, in green, whoa, that was not a good drawing. The Y vector going along the Y-axis, we're flipping it along the X, and so it's going to spin over 180 degrees and go into -Y. And so the matrix that describes x, y going to x and -y is 1, 0, 0, -1 using our matrix multiplication rules. We take the trace or the character of that matrix, and we get that chi of C2 operation is equal to 1 plus -1, which is equal to 0, which is exactly what we get for the E vector. So we proved now that X and Y have symmetry of E in totality. Okay, what about some of these quadratics? We can look at some of these simpler cubics that are pretty simple. Uh, maybe we'll do let's do a cubic first, actually, because it's just actually this cubic ends up being a little bit simpler. So I'm going to clear everything here, and let's do xz squared and yz squared. Well, we already know how x and y transform, and so if we think about how xz transforms, right? We know that x, well, an identity is not interesting, right? This is identity. It just goes to itself. Xc squared goes to xc squared. And we have a hint here because we know the answer that these are going to transform together. So we're going to have to, again, write a 2x2 matrix, this time with xc squared and yz squared, and them both going by themselves. We take the trace over that, and we get the same thing back, but we get a character equal to 2. So that's matching, but that's a little artificial at this point. Let's actually show that they transform together. So let's do the C3 operation. We know that X goes to, remember we have this rotation matrix, which came from cosine 2 pi over 3s and sine 2 pi over 3. So it ended up being -1/2. Sorry. -1/2. This is x, y. This was a rotation matrix for C3, 120 degrees rotation. -√3/2 and +√3/2. And we had -1/2. We had a sine 2 pi. Technically, it depends which way we want to do it, counterclockwise or clockwise rotation. Last time we actually did it this way. But anyway, it actually doesn't matter. The math will come out the same because C3 and C3-2 are in the same class, which are counter and anti-clockwise rotations, essentially, of 120 degrees. But let's now walk through how this works. So now we have xz squared. I remember from just earlier in the video, so okay, so x is going to -1/2 x plus √3/2y, and z, remember from earlier in the video, when you did C3 z on a z, nothing happened. So z just went to itself, and we have z squared, so z itself squared is just z squared. And so we get that, we can, factor that out, and we're going to get -1/2 xz squared plus √3/2y squared. And so what this is, yz squared, sorry, what this is telling us is that xz squared can only be defined in terms of a linear combination of xz squared and yz squared, therefore confirming that xz squared and yz squared do transform together. We can do the same thing for yz squared, and we should get the same sort of linear combination phenomenon with xz squared and yz squared. Y goes to, over here, looking at our transformation matrix, -√3/2 x minus 1/2 y, and then z squared still goes to z squared. So we get this same sort of setup here, where we get -√3/2 xz squared minus 1/2 yz squared. And now we can write our transformation matrix for this operation is xz squared yz squared times a 2x2 matrix, -1/2, with these coefficients that we figured out. -√3/2 and -1/2. And you can see what ends up happening is we have the same trace of the matrix, -1/2 plus -1/2, giving us the -1. So confirming this here. And we can do the same thing very quickly for the last operation, which is a C2. We were doing a C2 along the x-axis before, is how we defined it. And so when we do that, x-axis remains unchanged, but z changes, went to negative z. So that equals negative z squared is z squared, xz squared. And then if we do yz squared, well, y goes to negative y, and z went, because we're not rotating on the y, look at earlier in the video, think how we visualize that. So that's going to be negative yz squared. So we're going to have, again, we have to keep this as a 2 by 2 matrix because we know these two functions transform together. But we know that xz squared goes into xz squared, so we have 1, 0. And we know that yz squared goes into the negative itself, so we have 0, negative 1. And then we take the trace of this matrix, 1 plus negative 1, the character of this matrix equals 0. So we confirm now in totality that xz and yz transform together and they have E symmetry. All right, let's do one more. Let's do these nice d orbital functions, x squared minus y squared and xy. So very similar sort of thing here. Again, we have, let's just recall our rotation matrix for xy. This is for C3. We know we're going to need this. This was a negative 1/2 root 3 over 2. And then we had negative root 3 over 2 and negative 1/2. And so identity is not interesting. It just takes it to itself, but we're going to have a 2 by 2 matrix because we know from looking at the answer already that these transform together. The identity matrix is as such. We take the trace across that matrix, or the character across that matrix is another word for it. 1 plus 1 is 2. And now let's do it for the C3, which is the more interesting case. So now we have x squared minus y squared. So what does that transform to when we do C3? Well, x goes into negative 1/2 x plus root 3 over 2y. And that quantity, we have to square it. And then we have to say, do the minus y squared part. So where did y go into? Y went to negative root 3 to x minus 1/2 y, and we square that whole thing. Now we have a bunch of foiling to do. So we have this first term here, negative 1/2 x plus negative 1/2 times negative 1/2 x equals 1/4 x squared. We have this last term there, which is going to get us 3/4 y squared. And then we're going to have the intermediate terms, which together are going to add up as negative root 3 over 2, because we're going to have 2 root 3s over 4s, which combine to make a root 3 over 2 xy. And then we have to do this quantity. We have to remember we have this extra negative sign here. So this first component is going to be 3/4 x squared, but it's a minus, so minus 3/4 x squared. This last component here is going to be negative 1/2 y times negative 1/2 y, which is positive 1/4 y squared, but we have a minus there. So minus 1/4 y. And then our last component, we have two negatives times one another. It's going to be root 3 over 4. But we have two of them. And so that's going to get root 3 over 2. But then we have a minus. So we get minus root 3 over 2 xy. And so now we can combine like terms here. And so we have 1/4 x squared and 3/4 x squared. So that's going to be negative 1/2 x squared. And we have a positive 1/2 y squared. And then we have just minus root 3 xy. And so now we can factor out actually a minus 1/2. And that's going to get us minus 1/2 times x squared minus y squared. That's looking good. Minus root 3 xy. And so now we have come up with x squared minus y squared, how it transforms with the C3 operation as a linear combination of x squared minus y squared and xy. And that's showing us, therefore, that these two, we kind of prove that these two transform together. Let's do the back half of this. Let's now look at how xy transforms. Well, x transforms is the easier one of the two, as negative 1/2 x plus root 3 over 2y. and times by y, that's negative root 3 over 2x minus 1/2 y. We factor this out. We're going to get the first term is a root 3 over 4x squared. And then we have the last terms. I like to do these ones first. They're the easier ones to look at. Minus root 3 over 4y squared. And then we have these intermediate terms, sort of the harder ones to think about because we have to times it by 2. But this is going to be negative 3/4 xy, but we have 2 of them. So it's going to be sorry, actually, it's only going to be one of them at this point. So negative 3/4 xy, that's these inside terms. Well, let's now do the outside terms, which is going to get us plus 1/2 plus 1/4, right? 1/2 times 1/2 xy. Okay, and now we can combine like terms and factor. So we're going to end up with root 3 over 4 x squared minus y squared. That factors out very nicely. And then this becomes a negative 1/2 xy. And so at this point, now we have xy also transforming as a linear combination of x squared minus y squared and xy. Again, showing that these transform together. Now we can write our 2x2 matrix showing how this all works. And so we have x squared minus y squared at xy. And there's a 2x2 matrix here that we're not equals, that we're just multiplying by. And what is that? Well, for x squared minus y squared, it went into negative 1/2 x squared minus y squared and negative root 3. That's the off-diagonal component. For xy, it went into root 3 over 4 and negative 1/2. And so magically, you know, math is amazing. Everything works. We take the trace of this matrix, negative 1/2 times negative 1/2, and indeed we got negative 1, which is what we did all that work for. So it shows that so far we got, hey, we got a 2 here, we got a negative 1 here, we're tracking. Looks like we're going to transform as E. To fully prove it, we have to now do the last symmetry element, which is C2. When we were doing a C2, we define along the x-axis. So how does x squared minus y squared transform? Well, we know that x goes to x when we're doing a rotation, 100-degree rotation along the x-axis. So that just stands as y squared, x squared. And y squared went to negative y, or y went to negative y. So we have to square that, and that gets us back the same thing. So x squared minus y squared just went to x squared minus y. Now what about xy? Well, x went to x, as we just said, and y went to negative y. So in this case, we're going to the negative of itself. We can now very quickly write the 2x2 matrix that explains this transformation. And we know that x squared minus y squared is going into itself, so we have 1, 0, and xy is going into a negative of itself. We take the trace of this matrix, and we get 1 plus negative 1, which equals to 0. So we proved that x squared minus y squared not only transform together, but that they do so with E symmetry. So we've done a lot of these. You know, there's some more complicated ones here. Some of these you can figure out quite fairly rapidly. But really, you know, there's going to be much similar type of math going on here for these other more complicated cubic functions.